This is lecture 3. Today we'll be talking about atoms. We'll look at the historical development of the idea of atoms and see how through experiments and discovery we've come to the modern view of the atom. So we finished off last time talking about John Dalton, who proposed this idea of atoms. He originally thought of atoms as maybe being like billiard balls or pool balls with little hooks on them. So they were like hard balls that didn't change shape, they're rigid, but then they could also just kind of link to other balls and get stuck. But by the late 1800s and the early 1900s, as scientists experimented more and more with electricity, we found that this hard sphere model of atoms started to break down. And we started to find out that they are more and more divisible. And before we get too much into atoms, there's some physics we need to understand. Physics about repulsion and attraction of charged particles. Okay, when you have two charged particles, if they're both positively charged, like these two, symbolized with the by the plus sign in the middle of them, if you have two charged particles that are both positive, they're going to repel each other and try and get away from each other. But if one of those is negatively charged, as symbolized by the minus sign, then the positive and negative are going to be attracted to each other. Similarly, if you have two negative particles, they're going to also try and get away from each other. But the force of that attraction or repulsion is described by this equation, where F is the force, Ke is a constant that's just been measured. Q1 is the charge on particle 1, Q2 is the charge on particle 2, and R down here is the distance between the two charged particles. So if you double this charge right here, so if you double the charge in one of the particles, you'll double the force. If you double the distance between these, then this will increase by a factor of 4 because that's 2 squared, right? And since that value right there increases by 4 and we're dividing by the total strength of that force decreases by or to a factor of 1/4 the original value. So the strength of this interaction depends on both the magnitude of the charge on the particles and the distance between them. Right? So if these two particles though are free and not fixed in place, they'll come and crash into each other. And by 1900, it was clear that atoms could be broken into these parts that would be attracted and repelled by each other. One of the groundbreaking experiments that helped show some of this, or helped us to learn that some of these charged particles were actually existing inside atoms. And we now know that charged particles are either just charged atoms or parts of atoms pulled apart. But one of the fundamental experiments was performed by J.J. Thomson, where he took a glass tube, he sucked all the air out of it, he put some electrodes on either side of it, so some metal poles, then he attached this to a battery. Now, it had already been shown before Thomson that you could get an electric current to run through an empty tube like this. And so there's already postulated that there was some sort of current. But what J.J. Thomson did was he put this phosphor screen inside the tube. So this is just like a sheet coated in phosphor. And what happened was he started getting these fluorescent lines forming on these phosphor sheets as he shot this current, this electric current through here. So he said, I've discovered some new particle flying through here. And he wasn't sure if this was some sort of light or if there was some sort of ether wave, which we now don't really believe in the ether. But what also he tried after he saw these streaks in the paper was he put some plates on either side of the tube. He applied a positive potential to one side and a negative to the other. And when he did that, he noticed that this beam started curving towards the positively charged plate. So whatever was flying through here, scratching this phosphor paper, had to have a negative charge, because if it wasn't negatively charged, it wouldn't be attracted to a positive charge. So after he put those plates in there and curved this beam with positive and negatively charged plates, he then tried to curve the beam with magnets. So he put some magnets in here and found that that also curved the beam. And if you're going to curve something with a magnet, that means it has to have some mass. And so he was able to figure out from a bunch of equations we're not going to go into here, the mass to charge ratio, or specifically the charge to mass ratio of these things flying through here. And he was able to determine then that they did have actual mass. But he couldn't figure out the mass itself or the charge itself. He just knew how the two were related. And we didn't figure out the charge until a guy named Millikan came along. And in 1910, Robert Millikan carried out some experiments with the help of a graduate student named Harvey Fletcher. I'm going to highlight Harvey here because he was actually a BYU alum. He graduated here with his bachelor's and then came back later and eventually became our Dean of Graduate Studies. But Harvey and Robert carried out these experiments where they took a big metal container and they had a looking glass on the side so they could see inside, an X-ray source, and this pumper thing. I don't know the actual name of this, but a device where they could pump mist into the inside of this chamber. So inside the chamber, there's two plates, a top one and a bottom. And in the top one, there's a little hole where the mist from this sprayer can come down, okay? And then as that mist is coming down, we shoot X-rays across. And X-rays, if you shoot them into air, will actually dislodge electrons from the atoms in air, the oxygen, the water molecules in air. So when you spray this mist of oil down in here, the oil can then pick up those electrons. So now we have negatively charged oil droplets floating in this thing. Then we can apply a positive potential to this top plate and a negative to this bottom. Now, since we've got a negative charge on these, they're going to want to get away from the negative plate and get towards the positive plate, right? But there's two things going on here. One of them is gravity. Gravity is trying to pull these droplets down with a force equal to mass times the gravitational constant g. And then we have that electric field that we were just talking about that's trying to pull them all back up. And that force is equal to the charge on the droplet times the electric field. So now you have two competing forces here. If the electric field isn't high enough, these will drop, or the droplets will drop off and hit the bottom plate. If the electric field is too high, the droplets will come and hit the top of the plate. So you need a spot where the electric field and gravity are equally competing. So you can only get a certain type of droplet floating here, one with the right mass to charge. And so once those are balanced, you get a floating droplet in the middle here. And when these are balanced, you know that the charge on the droplet times the electric field is equal to the mass of the droplet times the gravitational constant. So we now have this equation describing what's going on in our droplet. Now we know the gravitational constant already. Newton figured that out for us a long time ago. And the researchers set the electric field potential, so we know that as well. And then we can just look at this droplet, measure its diameter. That'll give us our volume of the droplet. And they already knew the density of the oil they were working for. So from density divided by volume, they were able to get the mass in this equation. And now we can measure how much charge is on these droplets. And the results looked like this. So on different droplets, you'd get different amounts of charge. And I don't need you to memorize these specific numbers, but what you should notice is that they are all changing by about 1.6 times 10 to the negative 19th coulombs. That's the value between all of these. And that is the charge of a single electron. And so Harvey and Robert were able to figure that out. Now you don't actually need to memorize this number either, as it'll be on your equation sheet for exams, and you can look it up in the front of your book. Pretty much every science textbook has that number in the front of it now. Okay, but now we've decided that matter has some sort of negative component to it, but most matter is neutral. So if it's neutral and it has a negative component, that means it has to have a positive component to balance out the negative component. So now we're going to get into radioactivity. Okay, in 1895, Wilhelm Röntgen published his first paper on X-rays. So he found out a way of generating X-rays, and his first thought was, hey, wife, come here, stick your hand right here. And he took a picture of his wife's hand. So this is the first X-ray image, and it shows his wife's bones and her wedding ring, which they didn't realize at the time you should take off because it might reflect X-rays back into your eyeballs. But you know, it was a simpler time. It wasn't actually a simpler time. It was a time where the mistakes we've learned from now hadn't been made yet. And so these guys were the ones that made the mistakes that taught us how to use X-rays responsibly. The following year, in 1896, Henry Becquerel reported that uranium salts, which he had been studying, were also emitting some sort of rays that were similar to X-rays. But whereas Wilhelm had to use a device to generate the X-rays, uranium seemed to generate them all by itself. So then Marie Curie comes along and she studies uranium salts really extensively. And she found that parts of atoms had positive charge. She was the first to discover this, and she described in detail 3 types of radiation that was being given off by this uranium as it decayed, as we now know it. So what she did was she took a lead box, and inside she drilled a hole and put a little uranium sample. So rather than calling this a lead box, it's actually a lead cube with a hole drilled into it. So she put that uranium in there, and the lead would absorb all of the radiation coming off in every direction, except that coming out of this hole right here. And then she took a battery over here with a couple of leads. She attached the positive lead to one part of the battery, the negative lead to another. And then she noticed that there was something which she called alpha particles that were attracted to the negative lead. If they're attracted to negative leads, that must mean they are positive. And she found that they were fairly substantial relative to the negatively charged particles, which were going to the positive lead. We now know that the alpha particles, as she called them, these big guys, are actually nuclei of helium atoms, and these beta particles are electrons. And then there was this third type of radiation called gamma rays, which just shot right through and didn't interact with those leads at all. So gamma rays are just electromagnetic radiation similar to light, and we actually still call these gamma rays. We still use the term alpha and beta particles when describing nuclear decay, but in all other instances, we just call these helium nuclei and electrons. But she showed that matter could decay with both positive and negative components. And so she said that atoms must have both positive and negative subatomic particles. So then J.J. Thomson, a Brit, he thought, well, maybe the atom looks like a plum pudding. So in a plum pudding, you have raisins suspended in the pudding here. And he thought maybe you have electrons suspended like these raisins in a big positively charged blob. But in 1911, Ernest Rutherford, started playing around with alpha particles and shooting them at gold foil, and that found out something very different. So in Rutherford's experiment, so Rutherford was a New Zealand physicist, and he's made his way onto their currency and had a bit of a lifespan on there. But what Rutherford did was he shot alpha particles at some gold foil. And then he wrapped around that this phosphorescent or fluorescent screen that glows when it's impacted by alpha particles. And so what he was saying is, if I shoot these alpha particles at the gold foil, how much will they spread out? Now he just thought they would go through and spread out a little bit. But then these alpha particles started hitting the gold foil and just firing right back. And Rutherford described this as firing a cannonball into a piece of tissue paper and having the cannonball fly right back at your face. And that's paraphrasing. I don't remember the exact quote, but it's still fun to paraphrase. Now what this showed was that the plum pudding model wasn't going to work. So the plum pudding model is here on the left, where all the orange here is the positive charge, and you got these little negatively charged electrons. And in this model, if you have positive charge, it's going to deflect whenever it gets near to an electron. Most of it's going to be far enough away from electrons it'll just pass through, but some of it will be deflected, and so you'll basically just spread out your beam as it passes through this gold foil. But what actually happened, right, was things were bouncing back. Now you can only get that bouncing back effect if all the positive charge isn't spread out, but it's centered in one location. And so he discovered that all the positively charged stuff in the atom was confined to one space. And from the angles at which things were being deflected, he was able to determine that that tiny space was about 1/10,000th the size of the atom. So to give you an idea of what that means, I'm going to give you this iClicker quiz. So we know now that a gold nuclei is about 1 × 10⁻14 meters in diameter. And the distance, so that's one nuclei, and the distance between two nuclei, so two atoms sitting next together, they're each going to have a nuclei. And the distance between those two nuclei is about 3 × 10⁻10 meters. So if we wanted to create a model of aluminum foil using bowling balls, which have a diameter of about 22 centimeters, and we're going to use those as the nuclei, how far apart will you have to space the balls? Okay, go ahead and pause the video here, and then I will work through it in a sec. All right, so here is how you should set up this equation. It's a ratio equation. So what we have on the top are the two distances between the nuclei. So on the right here, I have the actual distance between two gold nuclei. And on the left, this x value, which is what we're trying to solve, is how far apart our bowling balls are going to be. Then on the bottom, we have the two diameters. All right, on the left, we have the diameter of the bowling ball, right, which corresponds to the distance the bowling balls are apart. Then on the right, we have the diameter of the gold nuclei, which corresponds to how far apart the nuclei are from each other, right? Now you might be asking, how did I know to put the distance between the nuclei on top and the diameters of the nuclei on bottom and not the other way around? The answer is you can do it both ways. It just changes whether you're multiplying or dividing by x, right? But then if we solve for this, we will find that the answer is 7.3 kilometers. So these bowling balls have to be pretty far apart. Is over there. 22 centimeters, which is pretty close to 10 inches wide, and then 7.3 kilometers, which is pretty close to about 3 miles apart from each other. All right, in 1914, or by 1914, Rutherford and a few other scientists were able to determine that the amount of positive charge in the nucleus of each element was unique. So carbon has a different amount of positive charge in its nucleus than nitrogen and chlorine, etc. And he was also able to determine that the amount of positive charge in the different elements varied by 1. So the difference in charge between carbon and nitrogen was 1. So carbon had 6 charges, nitrogen had 7, the next element had 8, the next element had 9. So from that, he was able to postulate that there must be some sort of individual positively charged particle. And I'm sure at that time they thought this was an individual particle too, but it's not. But there is individual positively charged particles. And in 1920, Rutherford discovered a particle that had the mass about equal to a hydrogen atom, but the charge equal and opposite to an electron. So there's this big positively charged thing that he dubbed the proton. And the proton weighs a lot more than the electron. So at this point, I'll introduce to you what's called the atomic mass unit, or AMU. So it's not very convenient to talk about nuclear or subnuclear particles or subatomic particles in terms of kilograms. So we use the unit AMU. And we've defined this as being pretty close to the mass of a proton. We'll get into how it's actually defined in a later lecture. But you'll notice that a proton weighs 1.007 AMU, whereas an electron weighs 0.005 AMU, right? So the proton is much heavier. It's about 200 times heavier than the electron. And so now we can say that each element is defined, or what defines an element is how many positive charges are in the nucleus. So the atomic number now becomes a thing, what we refer to as Z. The atomic number is generally listed on all periodic tables, and it lists how many protons are in that element. But there's still some stuff that's missing. For example, the elemental mass doesn't seem to correspond, at least not directly, to the number of protons in an element. And between elements, so between carbon and nitrogen, for example, their atomic mass changes by more than 1 AMU. It changes by 2. Some elements that differ in charge by only 1 change it in terms of atomic mass by 3 AMU or 5. So what's going on there? Even though they're changing by only 1 proton in the center. And to complicate things even further, sometimes the elements don't even weigh the same as themselves. So sometimes carbon, for example, will weigh 12 AMU, sometimes it'll weigh 13 AMU, and sometimes even 14 AMU if you get it from the right place. Now, I'm not saying that carbon's mass shifts. I'm saying that there is some carbon that weighs 12 and there's some carbon that weighs 13. And most carbon, in fact, almost all carbon that exists in the universe has a mixture of carbon-12 and carbon-13. And in 1920, Rutherford said, you know, we have to have some uncharged particle. And in 1932, one of his former students, James Chadwick, finally found this neutral species, and he dubbed it the neutron. And he found that the neutron weighs almost the same as a proton. It's slightly heavier. So the proton is 1.007 AMU, the neutron is 1.009 AMU. So now we have all of the components that are in the atom. We have the current modern view of the atom, where we have a small nucleus and we have a cloud of electrons around the nucleus. Now this model is actually going to keep getting more complex. We're almost to the point where common society understands the atom. We're actually going to go farther than that, and you'll realize that the common understanding of the atom is actually also false. All right, but let's zoom in now on this nucleus, right? The nucleus now we know is made of protons and neutrons, and we know it's really small. And we call protons and neutrons collectively nucleons. Now we have ways of describing individual atoms. So we have the atomic number, which corresponds to the number of protons. So in this nucleus, there are 2 protons, and 2 protons corresponds to the element helium. And we have a mass number, which is equal to protons and neutrons. So now we have a way of describing our atoms completely. What we said was the element is defined by how many protons are there, not by how many neutrons. So what happens if a neutron leaves? Well, now our mass changes. And this gets us into what are called isotopes. So isotopes are different atoms of the same element. So they have the same number of protons, but they weigh different amounts. So they weigh different amounts because they each have different numbers of neutrons in their center, in their nucleus. So helium-3 has 2 protons and 1 neutron. Helium-4 has 2 protons and 2 neutrons. All right, so here is our modern view of the atom once again, where all our protons and neutrons are at the center. The protons and neutrons weigh a lot more than the electrons, so most of the mass of the atom is in the center of the atom, and then you have a big spacious electron cloud around that. And if I give you here the diameter of the nucleus versus the diameter of the atom itself, you'll notice that the atom is about 5 orders of magnitude, or about 10 to the 5th times bigger than the nucleus. Okay, so up until this point, all of this is just looking at experiments that suggest very strongly that this is our model. But now, as of I think 10, 20 years ago, scientists started getting actual images of atoms. Now, we're not going to get into atomic force microscopy and hear how this works. If you want to do that, you'll have to take instrumental analysis. But each of these bumps is where an atom is. And then these white areas are valleys where there's nothing there. So the instrument's just not detecting anything. But we can now see individual atoms, and you can actually print atoms in individual spaces and write out words with atoms as your pixels, which is pretty impressive. All right, so I've thrown a lot at you so far. So we're gonna go on to an iClicker quiz really fast. I'm gonna ask you which of these experiments led to the discovery of the electrons. Go ahead and pause your video. All right, so let's walk through each of these. The cathode ray tube experiment is the correct answer. That is where we saw this new thing, could have been ether, but it was electrons. And we saw it being attracted to a positive plate. The oil drop experiment was then used to determine the charge of those electrons, right? Then the gold foil experiment told us that there was a dense positive center of our atoms called the nucleus. And then the radioactive decay experiment, well, that one just told us that matter can decay in both negative and positive ways, meaning that there had to be a positive component. But those are what those experiments tell us. All right, now let's get into how we represent different atoms of different elements. So here I'm giving the nuclide symbol for carbon. The nuclide symbol describes what's going on, not just in the nucleus, but in a single atom or in a population of atoms that are similar. So we have the mass number here, which is 12, which is the number of protons plus electrons. We have the atomic number, which is just the number of protons. We have the elemental symbol for carbon, which is the element corresponding to 6 protons. And then we'll either put a positive, a negative, a 0, or a blank space right here to indicate the charge. So the charge is determined by the number of protons minus the number of electrons. So since the number of protons are constant, we either gain or add electrons. Now we'll put a 0 there if there's no charge, or we'll leave a blank if there's no charge, because we don't need to indicate anything. It's implied. All right, so we talked about isotopes. And in isotopes, you have the same number of protons, but different number of neutrons. So it's the same element, it just weighs different. We have neutral atoms now, which is a term I'm giving to you. In neutral atoms, you have the same number of electrons as you do protons, right? So the positive charge of the protons cancels out the negative charge of the electrons. So what happens if you lose electrons? Well, now you have more protons than electrons, which means you have more positive charge than negative. You have a positive ion. So an ion is something that has either gained or lost electrons, and positive ions are called cations. Similarly, if you gain electrons, then you have more electrons than protons. This is a negative ion or an anion. And while most things in nature are neutrally charged, it's definitely not a supermajority. So for example, the Great Salt Lake is full of stuff that is both positively and negatively charged. Any salt is full of ions, full of positive and negative ions. Your body is full of positive and negative ions. The air around you is full of positive and negative ions. So ions are everywhere and they're extremely important. And we'll get more into that as the course goes on. Now, as we've said, the number of protons determines the elemental identity. So we don't usually record the proton count, or Z, and the elemental symbol. More often we just go with the elemental symbol. So let me give you an example of some simple questions I could ask you in this field, okay? So let's say I write something like this, bromine 79, okay? How many protons are in bromine? To answer that question, you're going to have to look at a periodic table. So let me pull that up. Okay, what I've got going on here is the periodic table that you're going to be given for exams. So it's going to look just like this. Now I have to find bromine on this table. So I'm just going to scan over it. Here's bromine right here. You'll notice this number 35 right here. That's how many protons are in bromine. So there's 35. And you'll notice this goes in order. So hydrogen has 1, helium has 2, lithium has 3, beryllium 4, 5, 6, 7, 8, 9, 10, right? And so these are just listed by how many protons they have. And we'll get into how we get into the column system a little bit later. But let me jump now back over to the PowerPoint. So we looked at our periodic table, and from there, we're able to determine that there are 35 protons on bromine. All right, so how many neutrons does bromine have? Well, we have bromine 79. We know this 79 is the mass number, which corresponds to the number of protons plus the number of neutrons. So we'd take 79 minus 35 gives us 44 neutrons. All right, how many electrons are in this? All right, we don't have a plus symbol or a negative symbol here. It's blank, which means this is neutral. For it to be neutral, it has to have equal positive charge and equal negative charge, or it has to have equal positive and negative charge. I guess right where it's that, which means we have the same number of electrons as protons. So we have 35. Well, how many electrons would we need if this were to be negatively charged? Then we would need at least 36 electrons. And you could have 37 or 38, and that would just change how many charges are on it. Let's see if you're following all of that. We'll finish with an iClicker quiz, where I'll show you strontium here and ask you what is the nuclide symbol for an ion containing 38 protons, 50 neutrons, and 36 electrons. So 38 protons corresponds to the element strontium. So go ahead and pause the video now, try to answer this question. All right, so the elemental symbol should be SR for each of these, and we notice that it is. You should have 38 protons in each of these. The protons are the bottom left number. Yep, each of these has 38 protons in the bottom left. We need to have 50 neutrons. So we have on the top left, we have 50, 88, 88, and 50. So is that number supposed to be 88 or 50? Well, we have 50 neutrons, but this isn't the number of neutrons. This should be the number of neutrons and protons added together. So it should be 88. So we know it's either B or C at this point. Now we ask, should it be 2 minus or 2 plus? Well, we have 38 protons and 36 electrons. So our charge is going to be equal to the number of protons minus the number of electrons. So 38 minus 36 is going to be a positive 2. So the charge is going to be 2 plus. All right. Hopefully you followed all that, and let me know if you have any questions.